Let's execute step 1 of the plan and prove that A mu is closed under complements. This one shouldn't be too hard. Alright, let B be a mu measurable set. Now we want to prove that the complement of B is mu measurable. Well, remember here was our definition of mu measurability. It's a for all epsilon type condition, right? So I want to start here by saying let epsilon be greater than 0. And then my goal is to find a set in our algebra of sets A such that the outer measure of the symmetric difference of that set with B is less than epsilon. Or sorry, not with B, but with the complement of B, since that's what I'm trying to show is mu measurable. All right, I'm going to start by doing it for B, since I know B is mu measurable. So there is some, using the mu measurability of B, there is some set from our original algebra of sets such that mu star of this symmetric difference is less than epsilon. Now, I guess it's intuitive to think that if B differs from A by something of outer measure less than epsilon, then maybe the complement of B will differ from the complement of A by something small. And in fact, what we want works at the level of set theory. B symmetric difference A is actually the same as the complement of B symmetric difference the complement of A. So this is just always true set theoretically, assuming A and B are subsets of X. So I know you know how to do the set theory argument, but I usually like to visualize things a little bit in this sort of proof by cases visually done. So in case you appreciate this, let's just look at a picture. B symmetric difference A consists of those things that are in B but not in A, and those things that are in A but not in B. So the union of these two green crescents. Then this other symmetric difference consists of those things that are in the complement of B but not in the complement of A, along with those things that are in the complement of A but not in the complement of B. Okay, so to be in the complement of B but not in the complement of A is to be in the complement of B and in A, right? Well, those things that are in the complement of B and in A are these things. And then those things that are in the complement of A but not in the complement of B are in the complement of A and in B. So what's in the complement of A, what's outside the A circle, and in B? Well, these things. Okay, so you see that they match up. That was probably not necessary, but for some reason it makes me feel better to do it. Anyway, that's pretty much it, right? Now mu star of, well, I guess one last part deserves comment. So this is now less than epsilon because it's literally equal to mu star of B delta A, right? And you should observe that this is actually in our algebra of sets. That's important too, right? So we have found something in our algebra of sets that symmetric difference with complement B has outer measure less than epsilon. So that's it for step 1. Maybe I'll put a box at the end of each step, and then I'll put a giant box at the end of the full proof. Okay, so you see why this mattered. This is using the fact that A is an algebra of sets. Remember, even if A is not an algebra of sets, we can still construct A mu, the collection of mu measurable sets. But when A is an algebra of sets, we find that the A mu that we construct does end up being closed under complements. So that was step 1.